Good morning, future presidents. There you go. You guys are back to vengeance. So, midterm number 2 on Thursday in class. Exact same format as the last midterm, so no big surprises. The practice midterm's already up. You guys have seen it. Solutions are up, so there won't be posted seating assignments. We had the rude discovery last time that they took all the seats, all the numbers off the seats over the summer. So they gave you nice new seats, but took all the numbers off. So we will probably have the GSIs just spreading you guys out when you come in for the midterm on Thursday. So don't be too surprised if they are telling you general areas to sit, but we probably won't be too specific about that. So any questions about the midterm before we go on with our new subject for today? Nothing. You guys are so prepared. Yes. How do gyroscopes work? We've got a lecture on that. You should look at that. Office hours. Come to office hours and we will talk. So gyroscopes. Gyroscopes. Who cares how they work? They're lots of fun. And they're cool. No, we'll talk. Come to my office hours or come to your GSI's office hours and we can talk about those. Okay, so any other questions? Yes. Relativity, is it going to be on the midterm? And because you were told it wasn't, did I say that? Who told you that? You don't know who told you that? Somebody told you relativity was not going to be on the midterm. That was not me. So, yeah, you should be prepared. It's on the practice midterm, right? So, yep, be prepared. Yeah. Yeah, we didn't, I mean, you know, we're not having you derive gamma factors or anything like that, so, but you should know the basic concepts, absolutely. So, and if you don't, then office hours, good thing. Okay, so. Okay, any other questions? I think I saw another hand back there, so, about the midterm. No? Okay, so by the way, it is, like I said before, it is focused primarily on chapters 4 up through electrical circuits, but that doesn't mean that you don't have to know anything about the first 3 chapters, so you need to understand those basic concepts. So we're building off of those concepts, so they are still important. Okay, so let's move on then with today's topic. Today we are talking about light. Primarily optical light. Okay, so remember, human eyes are sensitive to what we call optical light. Which runs from about, from wavelengths of about 400 to 700 nanometers. That is from the violet end of the spectrum to the red end of the spectrum. I remember when we had that big model of the electromagnetic spectrum here, we saw that that was a very small band, okay? But it's a very important band. It's the one that, of course, our primary sense, or one of our primary senses, works in. So optical light works over that very narrow wave band. Okay, so when we're talking about light and vision, okay, one of the things we're asking is how do we actually see an object? Okay, if there's an object sitting on that table or up on the ceiling, how do we actually see that object? Okay? And there are 3 ways that we see an object. All of them are require light to enter our eyes. Okay? So light from the object Okay, light from the object must enter our eyes. That's pretty easy. Okay, that's how we see something, light from the object entering our eyes. There are three ways that light from an object can come from an object to enter our eyes. Okay? The first is that the object is a source of light. Okay, examples of that, of course, are a light bulb, the sun, okay, a laser. So if the object itself is producing light, fire, that's another good one. If the object itself is producing light, then we see the light that is produced by the object. Okay? And the second way is the object reflects light from another source. And that, of course, is how we see most things in the world around us, not because they are emitting light themselves, but because they are reflecting light either from the sun or from the light bulbs in the room. Okay? So if the object reflects light, then that light scatters into our eyes, then we see the object. Okay? So this gets into the whole topic of color, which we're not going to discuss in any detail. There's sections of that in your book, but of course, the color of an object is not a property that is inherently of the object itself. So the color of an object depends on what color of light it's reflecting. So if an object is red, for example, that means that it primarily reflects red light. That means it's absorbing the other colors. So it's absorbing the blues and the yellows and the greens. Okay? So the redness of an object is how well it reflects red light versus the other colors of the spectrum. Okay? So, by the way, if you have a red object and you shine a light on it that doesn't have any red light in it, then the object doesn't look red, because there's no red light there to reflect off of that object into your eyes. So usually you will look kind of either black or brown or kind of muddy looking. Okay. The other way we can see an object is by forming an optical image. Okay. And this is another topic that your book goes in detail about. We don't have enough time in the course to go into much detail about it, but we'll summarize it real quick. So this is when we use lenses or mirrors. Okay, to form an image of the object. Okay, or when we use lenses and mirrors to, let me reword that so I'm not using the term image in the definition. Okay. Okay, we use lenses and mirrors to make the light appear to come from a new location. Okay, and the easiest example of this is when you look in a mirror. Okay, when you look in a mirror, okay, you see a reflection of yourself. That is an image of yourself that is in the mirror. Okay, you're not really in the mirror. Okay, that's just because the light has been reflected in a way to make it appear like it's coming from a new location, which is behind the mirror. Okay, so, and actually I have there's a fun little optical illusion demo here, which there's no way you guys can see it there, but I'll probably end class a few minutes early today to give you guys to study. And if you want to come down and look at this little optical illusion, it's pretty cool. So it's a little pig floating in air. So come down and take a look after class if I forget to remind you. Okay, so light. Light is how we see. Okay? Light is how images are made. Okay? But what is light? Okay, that gets to a very fundamental question, okay, which has actually been around for centuries. So the debate on what exactly light is actually goes back a long time, but Newton was actually, this is one of the questions that was driving Newton's original research. So Newton was actually convinced that light was a particle. So the question is, one of the questions is light a wave or is it a particle? It's something that's traveling. We know that it's carrying energy, okay, from one point to another. So example, sunlight is carrying energy to us here on Earth, okay, from the sun. But we know that energy can be transported either through, by a number of means. One is just through particles, mass, actual material being transferred here. Likewise, we know that energy can travel through waves. Okay. But all the waves we've seen so far require there actually be some medium for the waves to travel through. Okay. So light appears to be different. Light can travel through a vacuum. So light, that is a good reason to believe light might actually be a particle and not a wave. There's no medium for it to travel in. Okay. So Newton was actually convinced that light was a particle. Okay. And then all the laws of electromagnetism that we've been studying, okay, actually predict light as a wave, or they describe light as a wave. Okay. So there are, this debate on whether light is a wave or a particle has gone on for hundreds of years. Okay. And we're going to see in a couple of weeks when we get to quantum mechanics, so that's what we'll do right after the Thanksgiving break, that light is actually both. It's a wave and it's a particle. Okay. How cool is that? Okay. It's both, and it can be either one depending on whether you're trying to ask, is this light a wave? If you measure it, it will say, yes, it's a wave. If you say, is this light a particle? I'm testing it to see if it's a particle, then it'll be a particle. So the weird, wacky world of quantum mechanics. Okay? So that's something to look for in a couple of weeks. Okay, right now we're going to study the classical model. So this was the model of light that arose out of our study of electricity and magnetism. And that describes light as a wave. Okay? But it's an interesting wave because it doesn't require a medium. Light is a wave that travels on its own. It doesn't require any medium whatsoever to go from one location to another. And how that works, we've already saw the basis of that in our last lecture. So this is the electromagnetic wave model. Okay. And remember last time when we were studying magnetism, we saw that you can get magnetic fields that derive from electrical currents. And we saw there was a fundamental connection between electricity and magnetism, enough so that we've classified them as one force, the electromagnetic force. Okay. And we saw that most of that magnetic fields we can understand as deriving from microscopic currents, okay, in materials, or macroscopic currents in actual circuits. Okay. And the key that we saw last time was that electric field could produce a magnetic field, and a magnetic field could produce an electric field, okay, back and forth. And that's how we got the stuff floating, right? Stuff that we had levitating, or we were shooting those rings up into the air. It's because we were inducing a magnetic field that was producing currents. Okay? The currents come from the electric fields that are being created inside the material. And then those currents were creating their own magnetic fields, right, that were opposing the original magnetic fields. So magnetic fields, electric fields, they can constantly create each other back and forth. And this is the basic model for our electromagnetic wave. So light is a wave. Remember, a wave is just energy that's being transported. Okay? Light is a wave consisting of both electric and magnetic fields. Okay? And these electric and magnetic fields are constantly creating and recreating each other. Okay, it sounds almost like a perpetual motion machine. Okay, we've got electric fields creating magnetic fields. The resulting magnetic fields are creating electric fields. Energy is being oscillated back and forth between them. You can think of it almost like a mass on a spring, right? When we pull a mass on a spring, we're giving it potential energy, and that potential energy is converted to kinetic energy as the mass moves back towards its equilibrium position. Okay? And then that energy is converted back into potential energy as the spring compresses, so back and forth, it's oscillating. Okay? Same with the electromagnetic wave, it's just that energy is being transported. So this is a slightly enlarged model of electromagnetic wave. Okay? And the idea is that we have electric fields. Here it's showing the electric fields in the horizontal plane. So we have something that creates electric field. That electric field, once it's creating, will start producing magnetic fields. And that magnetic field will come back, produce an electric field, and vice versa. So we get waves, which are electric fields, okay, and magnetic fields. They're constantly creating and recreating each other, which sounds a little almost mystical. And it also sounds almost like a perpetual motion machine, except for there is a finite amount of energy that's going into this wave, and there is, at that atomic level, no way of dissipating it. So the energy has been put into the electric fields. It's got to go somewhere. It's going to travel along in the wave form. Okay? Now, there are a lot of specifics about how do you actually start creating the wave to begin with, and that's usually done by, for example, radio towers, which are producing electric fields. Radio towers are basically big conductors where we're literally putting a voltage on it, causing currents to flow, creating electric fields, which are creating magnetic fields, which are creating electric fields back and forth. Okay? And so the energy starts flowing out in electromagnetic waves. Okay? What's important for us to know is just that there is this basic process where electromagnetic fields, where electric fields and magnetic fields can constantly create and recreate each other, okay? Which sends that energy that we put into the fields propagating along. Okay? And it propagates along at the speed of light. So electromagnetic waves. The one thing that differs about this, okay, so these waves are similar to the mechanical waves we've already studied. They have a wavelength, they have frequencies, they have a speed, the speed of light. Okay. The big difference is that they don't require any medium. They are not vibrating any stuff. Okay? They propagate completely on their own, okay, from the electric fields and magnetic fields creating and recreating each other. So they don't travel through a material like all the mechanical waves we've already seen. They can travel on their own perfectly fine in a vacuum. Okay, so as long as there's nothing that is dissipating that energy in the electromagnetic wave, okay, usually comes dissipation by interacting with material, okay, just like light that is hitting us or hitting our eyes, that energy keeps on traveling. The energy has to go somewhere. It can't just magically disappear. It's got to be conserved, so it's got to travel, okay, until it interacts with matter. Okay, so let's start talking about some of the processes that light undergoes when it's interacting with material. For example, let's think about sunlight traveling to us. And what happens when it hits a surface? Okay, so this is light interacting with the surface. Okay, so here, let's imagine that here's a sun, and we're just going to shine sunlight down onto the Earth. And let's just look at a surface for, let's take, for example, water, since that's an easy surface that we're all kind of familiar with. Okay, so we've got sunlight that is traveling down from the sun. So let's put that as water, and we can ask what's going to happen to that sunlight when it hits the surface of that water. Okay. And, or if it hits any surface, we're just using water as an example. And it turns out there's three things that can possibly happen when that light hits. Okay. The first one is that the light hits and the energy gets dissipated in the surface, so that's just absorbed. So the light hits and just interacts with the atoms on the surface. It gets absorbed. So that energy, the energy of the light, is being transferred into heat in the surface. Okay. The next one, which we are also familiar with, is that the light can bounce off. Okay. Bouncing light, we usually have the name reflection. So the light can be reflected off the surface. Certainly we know water is a pretty good reflector of light. Okay. You can see how shiny it is when the sun's shining, and you can see your own image in the water. That's coming from light that's being reflected off the surface like a mirror. Okay. And the third thing can happen is that the light can actually pass in to the material and start traveling through. And if it passes into the material, then we have a name for that as well, because physicists have to rename everything. We say that it is refracted. Okay? So the light can be absorbed on the surface, it can be reflected from the surface, or it can be refracted through the surface. That just means it travels into the surface. Okay? And we know that light is refracted in water. You know that if you've ever swam in a swimming pool, because once you go underwater, you can still see, right? There's still light traveling around in the water that lets you see. Okay? It might not be as bright as it was when you're above, but there's still light that's going down through there. Okay, so different materials have different properties, but you could ask, given a certain type of material, which one of these processes is going to happen? And the truth is that for all materials, they all happen at some level. So let's see. Wei, can you focus on this? And we might have to turn the lights off up here to see this. That's pretty good. Okay. I'm buying that. You can almost see that. Okay, so what I've got here is this, basically it's just this cavity that's half filled with water. So here we got a surface of water, and I've got a source of light. So this, you can think of this as our sun moving across the sky over the course of the day. Okay? And we can look at what happens to that light when it hits the surface. We can ask, is it being reflected, refracted, or absorbed? And the truth is, for water going into light and water interacting with any material, all three processes are happening. Some of the light is getting absorbed, some of the light is getting reflected, some of the light is getting refracted into the material. And depending on the exact type of material, those different processes will happen in different amounts. Okay, but you can see, let's see, can you see? You can at least see on this that two things I think are obvious on this one. So this is light coming down from the top. And that is that when the light's hitting the surface, part of it is passing through. You can see the light continuing on into the water. If you're paying attention, you'll see that it actually changed directions when it entered the water. Okay, that's why we call it, we have a different name for it than just, entering the surface. It's refracted. It's actually changed direction. Okay. But you can also see that it's a lot dimmer once it entered the water. Okay. That's because some of it is getting absorbed at the surface. Okay. And the one thing you can't tell very obviously from this one is that part of it's getting reflected as well. Okay. That's a little bit more obvious if I come back and do it from the other direction. Let's come back from the bottom here. Okay, so this is light which is coming from the water. So it's traveling through the water, and then it's hitting the surface. Okay, this time this is the surface of the air. And you can see that the light is, in large part, passing through. Okay. You can see it's not getting nearly as absorbed coming through this direction for some reason, which I can't really explain to you. I had to think about that one for a while. Oh, I know what it is. Anyway, I've come to think about that. So the light's passing through, and you can see when it leaves the surface of the water, it's once again bending. It's changing direction. It's being refracted. Okay? But some of it is bouncing. If you look let's see, that depends on the direction. So there, I'm going to move the water up into there. You can see that most of that light is bouncing back into the water. We're going to come back to this in a minute when we talk about internal reflection and fiber optics. So you can see that the light can do a lot of different things when we go from one surface to another. It depends on the angle that it's hitting. Okay? But it's always some combination of those three processes, either being absorbed, it's being reflected, or it's being refracted. And refracted means it's passing through the material, and it's actually changing the direction as it passes through. Okay, so we're going to talk about those processes in a little bit more detail. So, and we'll come back to that in just one second. So let's talk about, first about reflection. So reflection is when the light bounces off of the surface. And this is our primary way of seeing objects in the world around us, because most of them are not emitting light. Most of them are just reflecting light from either the sun or from the light bulbs. Okay. So reflection. There are two different categories of reflection that I want you guys to keep in mind. So there is one that is called specular. Okay, that is reflection off of a smooth surface. And here you should be thinking about mirrors, okay? Reflection off of a mirror. So specular reflection is when we have a very smooth surface. And so when the light is scattered from a source, so let's say we've got light coming in from the sun or from some object up here in the corner. The light's coming in and hitting that surface. If the surface is very smooth, then all that light will get reflected in the same direction. Okay, it'll all bounce off. Okay, and stay moving in a nice same direction. So it all's coming in at this angle, and it's all reflecting up in that angle. So all the light reflects, it stays together in the same direction. And so let me write that out. Light is scattered in light is scattered in one direction, and this is how, from a smooth surface, we can see images in it. Okay? So if you can imagine that that light is coming from an object up here. So let's say we've got a candle or something up here that it has a light. Okay? it's coming down and it's bouncing off. And if you're up here looking at it, you'll see all that light coming to you from this direction. Okay? And that makes it look like the object is sitting down below here. So this is how, from a very smooth surface, we can get specular reflection, okay, which makes the surface nice and shiny, and it means we can see images in it, okay, because all the reflection is coming out of here with the light scattered in a single direction. Okay. We can compare that to scattering a light off of a rough surface. So this is diffuse reflection. Okay. And this is scattering off a rough surface. And here, when we mean rough, we are talking about at the microscopic level. Okay. So at very small levels. Okay. So this actually is the type of reflection we get off of most surfaces. Okay. And so you can imagine if we have a very rough surface and the light is coming in, so the light might be coming in from one specific direction, but it could be scattered out in all different directions. Okay? So the light is not scattered in one direction like for specular reflection. It comes in and it's scattered in all directions. Okay? So okay, so that means that we don't see images formed in the surface anymore. Okay? And that is true of most of the surface around us. The light's coming in, it's hitting it, and it's reflecting, but it's reflecting out in all directions. Okay? So, for example, when you're looking at the, I don't know, if you look at the seat next to you, you're not seeing an image of the lights in the seat. Okay? That's because the light's reaching your eyes from all different directions. It's not bouncing coherently off of that. Okay? Whereas if you look at the reflection off of a shiny object like the plastic or any glass in here, you'll see a reflection of the lights coming in because the reflection is specular, so it's letting the light all look like it comes from one direction, so it's forming images of whatever is the light source that's bouncing off of that object into your eyes. Okay. So when light gets reflected, okay, it can be selectively reflected, meaning that depending on what the surface is, okay, we can have light that some fraction of the light is reflected, like we saw in this little demo. Some of it can be absorbed, okay, and some of it can be refracted, just keep on passing through the material. Okay. And depending on what is actually reflected, we can get selective absorption. Okay, so the basic idea of this is that some colors can be preferentially absorbed. When other colors are preferentially reflected. And it's those preferentially reflected colors that will determine what color the object is, or what color it appears to our eyes, okay? Because it's reflecting the light preferentially at those wavelengths. Okay, this leads entirely to our understanding of why the sky is blue. And also why sunsets are preferentially red. Okay? And the very simple explanation for that is that air in the atmosphere preferentially scatters blue light. Okay, that's all you need to know to understand why the atmosphere, why the sky appears blue and why sunsets are red. Because the air, okay, it is preferentially will interact with blue light in sunlight. So remember, sunlight is a thermal spectrum. It's a broadband spectrum. Light come from the sun has all colors in it. Okay? And so it naturally appears very white because all the colors are present in there. Okay? So the colors we see from the sun comes from actually how the sun is interacting with the atmosphere. And that biases the color that we see from the sun. So let's draw a picture of that. Okay, so let's say here's the sun once again, and here's the surface of the earth, and there you are taking a nice walk on a nice sunny day. Okay? And let's imagine that we're on a sunny day with no atmosphere. So it might not be a very long walk, okay? But you'll get a lot of sunlight. Okay? And if we draw what's happening to the sunlight, then we would get all colors of the spectrum coming down and entering your eyes directionally. And what the sky would look like would be that we would see a very bright white sun, because all the colors are reaching your eyes. Okay? And then the rest of the sky would be black. We would see the stars. Okay? If there were no atmosphere there, then we would not get the sky being blue, which is what blocks the other stars coming. So we would see directly the light coming from the sun. The sun would appear very white, and there's no reason we wouldn't see all the other stars, except for if you're looking at the sun, it's going to hurt your eyes. So if you look away from the sun, even though the sun's up, if there's no atmosphere there, we would still see all the rest of the stars. We'd still see their light coming directly to us. So the sky would appear mostly black, except for the starlight reaching us directly. Okay? So, of course, that's not what we see when we go outside, and that's because the atmosphere has a very major effect on how we view light coming from the sun. So what really happens is that we have an atmosphere. Atmosphere is composed of air, and that air preferentially will scatter blue light over red light. So let's draw that picture again. Okay. Once again, here you are taking a nice walk in the afternoon, say, except for now we've got the atmosphere above you. Okay. So now let's look at the light again. So red light coming from the sun pretty much just comes straight through with very little interaction in the atmosphere. Okay? So that means that you will see red light. I could have drawn that with red chalk, but next time. So you'll see red light coming directly from the sun, okay, and entering your eyes. Okay. You'll also see, yellow and green. So the sun will look preferentially on the redder side of the spectrum. So our sun looks redder, and it looks redder towards sunset, which we'll come back to in a second. Okay? But it doesn't look white, right? Our sun doesn't look white. It's because a lot of the blue light has been removed. So let's see. I do have blue chalk. Now the blue, so the blue that would come from the sun directly to our eyes, okay, tends to get scattered. The atmosphere will scatter blue light very easily. So that stuff that's coming directly from the sun gets scattered off into other directions in the atmosphere. Okay. So this one will get scattered off into some other random direction, and light up here will get scattered off into some other direction. Okay. So that light coming from the sun doesn't reach us directly. So when we are looking at the sun, please don't look at the sun. If you're looking towards the sun, the blue light that would be coming from the sun to our eyes, okay, isn't reaching us directly. It's getting scattered out of the line of sight. So that blue light isn't coming from the sun, but it is bouncing around the atmosphere. Okay? It's not getting absorbed, it's getting scattered, it's getting reflected. And that reflected light will come and enter our eyes, but not from the direction of the sun, but from the direction, all the random directions it's scattering. It's diffuse scattering in the atmosphere. It comes in every direction. Okay, so we do get blue light from the sun entering our eyes. It's not coming from the direction of the sun, though. It's coming from the direction of wherever it's scattered in the atmosphere. Okay, so all that blue light is coming from random directions in the sky, okay? And that's what's making the diffuse blue sky around us. Okay? It's all the scattered light we're seeing, not the direct light from the sunlight. So, a couple things about this. First off, that light is, it tends to be pretty bright, but it's not actually blocking the starlight above there. So, if, so all that light from, the little stars twinkling up there is still traveling to us through the atmosphere even during the day. It's just that the sky is so bright with all that reflected blue light that we can't see it directly. But there are experiments you can do, like if you go to the bottom of a very deep well. I wouldn't recommend you do this. You could also do this with a very long tube. Okay? And you look up, okay, through that well, then most of the blue light that's being scattered around the atmosphere isn't able to enter your eyes because it's getting blocked by this well. Okay? And if there's a little star passing overhead, you can actually see it directly, even in the bright daylight. Okay? So it's because you're not getting all that glare from the atmosphere around you. Okay? So the blue sky isn't actually blocking any of the starlight. We just can't see it because the sky is so bright with all that reflected light. Now, if we think about the geometry of this, the Earth has an atmosphere, and the Earth is round. So let's say here you are once again on the surface. Here is the atmosphere, Earth's atmosphere above you. And let's think about the sun during different times of day. Okay? At noon, the sun is directly overhead. So it's shining down, and so light from the sun is reaching you straight through the atmosphere. Okay? But at sunset, so let's imagine the sun is way over here. Now imagine that this board is about 10 times longer. So the sun is coming at you as it's heading towards the horizon. Okay? The light has to travel through much more atmosphere to get to you from the sun. Okay? As it travels through more atmosphere, the light has a longer path in the air to interact. That means more and more of the blue light's getting scattered. In fact, more and more of all the short wavelength lights are getting scattered. And what's left is the light that is least likely to interact in the atmosphere, which is the red light. Okay? So that's why the sun, as it's heading down towards the horizon, looks redder and redder. And that's why the sunset is very, very red. Okay? That's because as the sun goes down towards the horizon, it's got more atmosphere to pass through to get to your eyes, okay? Which means more and more of the blue light is getting scattered out of the sunlight, which makes it redder and redder. Okay, so very simple understanding of why the sky is blue. Okay, any questions about sunlight? Blue skies, yes. Sorry, can you say that again? Why it's the sun is brightest. So the question is this why the sun's brightest at noon? So yes, absolutely. So I mean the atmosphere does absorb some of the sunlight as well. So it's just not a huge fraction of it. And so the more atmosphere it has to go through, the more and more will get absorbed. And so the sunlight that reaches us at noon is brighter when it's right overhead. So there's also there's a geometric effect there too, which I won't go into too much detail about, but let me draw you a quick picture of that. So when the sun is shining down, directly overhead, let's imagine we got two light beams coming at you directly from overhead, right? So those take up an area on the ground which is, has some diameter to it, right? If those same light beams are coming from at this very off angle, okay, they still have the same, separation, but their projection on the ground gets to be much bigger, which just means that the light coming from this angle, from a very shallow angle like this, is effectively getting spread out, which makes it look dimmer. So that's just a geometric effect from the angle that the light's hitting the surface down here. So that will also make it dimmer as well. So if that makes sense. Yeah, that's a great question. So, yes? So let me see if I understand your question. So your question is if you put two mirrors right in front of each other, so like these are like the barbershop mirrors, right? So when you're sitting there and you can see the reflections back and forth, and then in this mirror you're seeing this reflection, and then you're seeing that reflection, so it makes sort of that infinite thing, right? So if none of the light were getting absorbed, then that reflection would go on basically forever, right? But every single reflection, remember, every time the light interacts with the surface, some of it gets reflected, some of it gets refracted, and some of it gets absorbed. So there's going to be some fraction that gets absorbed there. So that means the image is going to get dimmer and dimmer as you go along. So it definitely gets darker as you multiply those images along. So did that answer your question? Yeah. Uh-huh. I see. So if you look at an angle, the reflections get darker? Yeah. I'd have to think about that. Maybe you could, yeah. I'll try that experiment and see. But it's probably just because they're getting more and more absorption coming in. So remember, so the way that, mirrors are usually built is that there is a layer of glass, and glass by itself isn't reflective, right? So glass mostly is transparent. And then there's a very thin layer of some very shiny metal back here. So for cheap mirrors, it's aluminum, and for fancy mirrors, it gets to be silver or some expensive metal. So this is glass, and this is metal. Okay? And so, sorry I can't lift this board. It's a small group over here that probably can't see this. So if you think about the angles are coming in, right? So when light comes in, it's getting actually reflected in that mirror off of the metal in the back. The glass is there primarily just because it's a very smooth surface. And so you can make the glass very smooth, and then when you put the metal on it, the metal is very smooth on this surface between there. So the glass makes the metal very smooth surface for reflection. So you get nice specular reflections off of that surface. I mean, you can get reflections just off of metal by itself, but they're not so nice, right? Because they're still rough. So the glass here is just providing a smooth surface to put the metal on, right? So, but you think about it, when you're coming down at an angle, like if you're looking at the side, you're getting this exact same effect that you get from the atmosphere, right? So you start looking at reflections of light that are coming in, you know, at a very shallow angle, then that light is traveling through much more glass, so more of it could get absorbed. So my guess is there is a noticeable effect, even though I've never noticed it, when you look at a mirror at an angle, that it will get dimmer because more of the light will get absorbed in that glass that's traveling along. So that's a cool experiment that we can all try at home tonight. Good question. So let's see, I saw some other hands though. Is there any more questions on this? How many times do you get to ask why the sky is blue? Okay, well let's move on then. So we've talked about reflection. Now let's talk a little bit about refraction. So remember, refraction is what we call it when light travels into a medium and continues traveling through it. But refraction is, I'm just going to use these boards, has one additional effect, which we already saw in our little demo, which is that the light doesn't just go into the new surface, in this case the surface of the water, the light actually changes direction. And that has some very important applications. So remember, this effect is called refraction, when light is traveling from one surface into another surface. Okay? And there's a very important effect that's going on here, which is actually causing the light to turn, which is that light travels slower. In any material. And a general rule, even though this isn't absolute, is that the denser the material is, the more slowly the light will travel. Okay? And it's the fact that the light is actually slowing down when it enters the surface, which is why it's turning. And this is the reflection. Okay? So the fact that it's slowing down will actually turn the light. So it will actually change direction because of this. Okay, so that's the same thing as if you can imagine you are riding, I don't know, let's say you're roller skating on a very smooth, nice hardwood floor, right, at the roller rink, and you're coming in at an angle, okay, and suddenly you hit their nice shag carpet they have out in the waiting area. Okay, so you're coming in, you hit that shag carpet, and suddenly you are slowed down, right? But you're preferentially slowed down in 1 foot before the other, right? So when you enter that slow medium, it's actually going to turn you. Okay? Effectively, the same thing is happening with light as it travels into a new medium. It moves into a new medium, it slows down, that new medium slows it down, it will turn it into a new direction. And so that is refraction, and it has one nice feature, which is that short wavelengths will turn more than long wavelengths. So violet light will turn more than red light when it enters a new medium. So yes. Yes. Lots of implications for special relativity. So, but not as many as you might think. All the laws of special relativity we derived were for in a vacuum. And so when light enters a medium, say light's traveling through glass and it slows down, then we actually can have the situation where particles can move faster than the speed of light inside that medium. And it has some pretty interesting physics effects, but they're not nearly as fundamentally cool as you might think. So stuff that travels faster than light inside of a material like glass will actually produce its own light. But it's not violating, time, direction, or anything like that. So that's only in a vacuum where we get those funky effects that come in. So in a material, when light's traveling through a material, it's perfectly okay for particles to travel faster than that light in that material, but they still can't travel faster than light does in a vacuum. So, but there are certainly interesting effects that happen, but they're not like strange time dilation or anything like that. So, yeah, that's a great question. So, thanks for asking that. Okay, so light bends when it enters a medium. Violet light will turn more than red light. And that is how prisms work. So you've all seen covers of Pink Floyd albums, I guess, where you have white light entering into a prism and diffusing out. So that's because the different colors are bending. Some violet is bending more than the red and diffusing outwards. Okay. So this is also how rainbows work. Okay, rainbows work because light spreads out differently when it enters water, in this case, raindrops. Let me see if, let me show you the demo of this and then we'll draw a picture of it. So, what I've got here is a model of a rainbow. In the back here, I've just got a very bright light. It's a white light. Okay, so this is just a white light we've got shining through there. So you want to imagine that is the sun. Okay. And here I've just got a circular beaker of water, which is basically just a big raindrop. Okay? So what's happening is that the light is entering into this raindrop, which is just water. And sorry, is that shining right into your eyes? I'll go off in a second. So the light's coming in. Okay? The different colors are getting bent differently when they enter into that raindrop. So the violet's getting bent more than the red. Okay? It's coming in, and it hits the back edge of the raindrop. Okay? Remember, at any surface, we're going to get some light that's refracted, some that's absorbed, and some light that's reflected. So it's the reflected light that is interesting us here. So light comes in. Okay, it bends and spreads out. So the violet bends more than the red. Okay? It comes and hits the back surface of the raindrop, which is right there. I'll put my hand over there. So it hits that back surface, and some of it bounces back in the direction it came. Okay? But the direction that it actually bounces will depend on its wavelength, because the different wavelengths are coming in and spreading out at different things. So what we see is back behind the raindrop, right? We're getting different colors of the spectrum spread out there. I know that isn't showing up too well on the video. But we can see, for example, in this inner ring, you see the red, yellow, green, blue, and violet. Okay? It's forming a ring around here. Okay. So now what happens, you want to think about the geometry of this, which is how we see a rainbow, which is that the light is reflecting back in this direction. So when we see a rainbow, it's because the light is behind us, right? The sunlight is behind us. It's coming up and it's reflecting off of raindrops up there in the sky, and it's coming back and bouncing into our eyes. Okay. You can also see something else here, which is cool, which I won't go into too much detail about, but there's a second rainbow on the outer edge. So there is an inner rainbow here, And then there is an outer rainbow here. Sometimes on a very, very bright, clear day, you can see double rainbows up in the sky, right? And if you pay very close attention, the colors are inverted between the two. So they're flipped directions between the two, right? And this is coming from light that is bouncing twice here instead of once. Because every time it bounces off of a surface, it has a chance of being reflected. So it's coming in, it's getting refracted, spreading out, it's bouncing off the back surface, it comes to the front surface, some of it leaves and forms a primary rainbow, some of it will bounce back. Okay, and once if it bounces back again, it can form the secondary rainbow there. So let's draw a picture of that. Before I electrocute myself, these lamps are really scary. Just like, person setting up the demo is like, only touch that with one hand, please. We want to keep all open circuits up here. Okay, so let's draw a picture of this raindrop so maybe we get a better feel for how the light is being reflected in it. Just want to make sure I get the angles about right here. There we go. So here is our raindrop. Okay. And that is up in the sky. What we've got is the light coming in from the sun. So here is the sun, and this is white light. Okay. So that light is coming into the raindrop up on the sky. And the part that enters, remember, it's being refracted, so it's bending, but the violet light will bend more than the red light. Okay? So when the light enters the water, it'll start spreading out. So we'll get the violet light bending more than the red light. Okay. So let me see. I actually could use colors on this, right? So there's violet. This is roughly reddish. Okay, so the red light's going to come and it's going to bounce off. Okay? It's going to bounce off the back, and then it's going to come and pass through. Okay? It gets bent a little bit as it passes through, okay? But it basically leaves the raindrop. Okay? That light that's been reflected will come back in the direction that it originally was, but it'll be bent a little bit from that. Okay, likewise, the violet light, which will here be represented by blue, it will come out. It's been bent more when it entered the raindrop, so it's going to reflect off of a different position on the back. That reflection is at a different angle. Okay. So that means it's going to be coming back out at a different angle from the red light. Okay? So that light, which was white when it entered that drop of water, is being spread out and reflected at different angles. Okay? So that means if you are sitting down here on the ground observing that, okay, you're going to see the light that's reflected into the direction of your eyes, right? So this particular raindrop is only going to reflect specific wavelengths into your eyes. In this case, the way I've drawn it is more in the red side, right? So let's draw this coming all the way down. So there's the red, and there's the blue, right? So the way I've drawn this one, the red will be coming from this raindrop and hitting your eyes, but the blue or the violet is going to be missing them, right? Because the angle isn't right, okay? Well, there's other raindrops. Those other raindrops have the right angle, right? In this case, it would have to be a lower raindrop in the sky, right, that reflects violet light into your eyes. So here's the other raindrop at a lower altitude that's doing the violet reflection into your eyes. Okay, so that will produce a band, right, the rainbow, across the sky, where the higher ones will be producing the red light, will be bouncing the red light in your eyes, and the lower raindrops will be doing the purple ones. Okay? And the geometry for this is that the sun has to be behind you, right? So the sun has to be shining behind you into that raindrop, okay, or onto all those raindrops and reflecting the light back in your direction. So you're going to see the different colors coming from the different directions, which is the basics for a rainbow. That's nice. Okay. So that is one cool demo of refraction. And this is a little bit more of a practical application. So let's, I'm going to have the water. Let's see, can we zoom in there? Great, thanks. Okay, so let's start with it like this. So you can see that I've got the light here, and it's traveling through the water, right, through a denser medium, and it is refracting out into the air. And in this particular angle that it's coming in, most of that light is passing out into the air, okay? So it's leaving the medium. Now, refraction has an interesting property, which is it bends the light, which means it comes out at a different angle, and you can see that the angle it comes out there, okay, it's bending more as it gets into the air. At some point, it's going to bend at 90 degrees. And so there's going to be a limit to how much light can pass out of that surface. And once we hit that limit where it would be reflected, where it'd be refracted at 90 degrees, the light can no longer pass out of that surface. And you can see that it's all reflected. Okay? So if you can see that on the demo, you can see that most of the light's being refracted out. Okay? And then the angle that it's refracted is as it gets to be parallel to the surface, it can no longer leave, and all that light is getting reflected back in. This phenomenon occurs when you have light that's trying to leave a denser medium into a less dense medium. And there is this limit on the angle that it's traveling along that surface where all of the light gets reflected back into the surface itself. Okay. So we have a name for that. It's called total internal reflection. And it has a very practical application. Which is fiber optics. Okay, so in total internal reflection, the light can stay trapped in a denser medium. And that means that it will stay and have to propagate along that medium itself. So, and this has a very practical application in fiber optics. Okay, so and let me show you that. So here is our denser medium. Okay, so this is just a plastic, so it's a plastic tube. It's solid, so it's not hollow. Okay? So you can kind of think of that as the water here. Okay? And so if I shine light into this, okay, if it's not coming directly up and down, if it's coming at an angle, then that light's going to all reflect off the surface when it tries to leave. So all that light is going to be trapped inside there. Okay? So when I do that, I got a laser here, which is green. See the green light there? Okay. I'm just going to send the light along there. And what you're seeing is there's always a little bit of light that scatters out if it gets scattered at a funny angle. But most of that light is being trapped inside the surface. Okay? It's being trapped inside the tube, and it's actually being forced to travel along the tube in this spiral. Okay? And you can kind of see, let's see, let me put a piece of paper up to it. There you go. You can see the light leaving the end of that tube. It's actually been turned not only in those circles, but it's turned at 90 degrees here at the end. Okay? And you can see it leaving the end of that tube. Okay? So the light is basically effectively trapped inside this piece of plastic. So this is the basics for fiber optics, okay, where we actually a lot of communications even today, but certainly going forward, instead of sending currents in copper wires, copper is very expensive, plastic is very cheap, okay, and light travels really fast, so we can start sending signals along fiber optics tubes. Okay? And the fact that there's this property of internal reflection, total internal reflections, means that we can actually use pretty low power, right? Because all the light is being trapped in this tube. It's not being dissipated through resistance like currents are. So we can do very low power, very fast signals traveling along these tubes, okay, where the light has actually been trapped. And that's the basis for fiber optics. And those plastics can be made a lot cheaper than copper, which is actually pretty expensive metal to produce. So you will be learning more and more about fiber optics as you go forward. Let's see, we've got 5 minutes. I think I will just say something very shortly here about lasers, and then I'll let you guys go. So lasers are light. But they are coherent light. So what do we mean by coherent? Let me just write that word down. Okay, lasers are coherent light. By coherent, we mean two things. So all the light has one color. See, this laser is green, very single, very one wavelength. It's all coming out. Right? It's not like sunlight, which has multiple colors. Okay? And all the light is traveling in one direction. So that light stays focused into a very narrow beam. So that's all pretty obvious, okay? But the implication of it is that we can make this very intense, because the light isn't spreading out. That energy is staying focused into a very fixed direction. So that means we can produce very intense beams of light, which leads to all the applications. So we'll try to talk about those at the beginning of class next Tuesday for a few minutes. So we will see you guys on Thursday. If you guys want to see the little floating pig demo, feel free to come down, check this out.